Hello, everybody, and thank you for attending the hello again, everybody, and thank you for attending the fourth in our series of courses in on the UNESCO Chair in Disaster Risk Reduction and Resilience Engineering. Today, the short course will focus on fragility and vulnerability assessment. The course supports a number, the UNESCO Chair program supports, sorry for the slight problem at the beginning, supports a number of courses that we have started now in April, and as we say, we are in the fourth one of these deliveries that are aimed at disseminating and empowering people in assessing school infrastructures in an engineered and technical way in order to appreciate the vulnerability that associates with school compounds and school infrastructure exposed to different hazards, and identifying possible mitigation techniques. As you can see, we have quite a packed program also going into the autumn seasons and early next year, with more courses delivered by our collaborators as well as and partners such as the OASIS course as well as ourselves. You will find update on these programs on our website, which you can access at UNESCO Chair in DRR&RE at UCL Epicenter. Sorry, there is a problem with changing the slide. So today's schedules, or today and tomorrow's schedules, the whole course covers has 2 sessions, today from 2 to 4 o'clock and tomorrow from 2 to 3 o'clock, UK time, but of course, very many different times where you are listening from. I will provide a quick introduction to the seismic analytical fragility and vulnerability assessment, giving you a little bit of background so that you can best enjoy in context, so that you can best enjoy the following lectures. Then we will revert to, for the ones of you that have already attended previous lectures and courses, which again, you can find all online and on our YouTube channels. We will revert to the GLOSI framework, which I will recap quickly on, to explain what is the specific fragility and vulnerability methodology that we adopt. And then from there, we will really get into the nitty-gritty of delivering, of performing pushover analysis, and then using the N2 methods in order to determine the fragility functions. So we will then provide you with introduction to both the derivation of fragility functions and vulnerability curves. And at the end of the day, you will be entertained, or you will be given a task, which we hope you will take seriously and perform ahead of tomorrow, that will give you the opportunity to verify how much have you learned from what we have explained today. It's very much hands-on. So, and then tomorrow there will be times for checking the results and having an in-depth discussion before some closing remarks. So It's very important that you follow both days. It's very important that you perform the tasks. And at the end of the course, you will receive a certificate of attendance on the basis of having attended both sessions. So without further ado, I'm going to explain what is the roadmap to seismic fragility and vulnerability. Some of you might recall that I already used these slides to introduce the concept of the comprehensive school safety framework 2022-2030. This is been brought together by the Global Alliance for Disaster Risk Reduction and Resilience in the Education Sector. Pillar one of this comprehensive school safety makes much emphasis on safer learning from facilities. The need here is to really improve the environment and the buildings within which education is delivered. When we look at the diagram on the right, we have already spoken about exposures in the course that we delivered in July. We now want to look at the second component of the equations that determines risk, the vulnerability. And we know that when we intersect vulnerability, exposures, and any specific hazard, then we can compute risk. And therefore, from the risk that we have identified, we can understand where is it that through improving safe learning, improving, having risk reduction and resilience education, and improving the school safety educational continuity, we then arrive at resilience in the education system, not just in the buildings that we deliver. In order to pursue that, just a little bit of the size of the problem. So what we see here is a map of the world, and the larger the blocks, the higher the losses in terms of damage and in terms of loss of life, or with respect to the school sector. This diagram on the left identifies the direct damage from education sectors, and we can see that in some cases can be up to in excess of 20% of the total damage losses, and we can also see that this is very much differentiated between different parts of the world, and most affected are the Caribbean and the Southeast Pacific. This is also reflected in the colors that we can see here. So we can see that in some of the countries like the US or China, the color is quite dark. It means that in monetary terms, the expected annual losses due to earthquake are quite large. But indeed, in terms of what happens with the affected populations at school, the distribution is very different, because the vulnerability of the thing is very different. The vulnerability of the infrastructure is very different. So this explains why vulnerability is critical for safer schools. The school infrastructure is already there and is being used every day. So, and many of these buildings are not safe. Each school building has its own vulnerability. Again, when we look into the exposures, we know that there are many different building typology, and each of them performs a response to earthquakes in a different way. And so every single school building type might actually need improvements and can be made safe. How do we do that, and why have we chosen GLOSI? So when we want to determine a plan of retrofitting and improvement, then we need to start from the diagnosis, having a good idea what is the school infrastructure's baseline in a country and what are the policies to maintain and improve that infrastructure. We need to understand what we call the construction environment, the financial environment, and the risk and resilience assessment. Once we have these terms, so the what is possible to build, what are the technologies that are used in a particular country, and how these technologies are confidently used and delivered. And once we know what are what is the financial environment, i.e. what are the possibilities, the economic possibilities within the country, then we can start designing intervention strategy, and we can make investment plans, and we can then eventually implement such plans through an appropriate and robust strategies. In the previous course, we already spoke about taxonomy and about the need, the way in which by defining a taxonomy, collecting data, we can create the school infrastructure baseline. The school infrastructure baseline then allow us to deliver a catalog of building types, as we have already seen. Once we deliver that catalog, then we can, it starts understanding through analysis and resilience assessment and risk and resilience assessment, what is the fragility of each particular type and what is the vulnerability of that type. And once we understand that, then we can get to determine the vulnerability and reduction solution. So this is the process, the process that we will go today, and the topic of this particular lecture is relating to this third circle here, to this third steps in the GLOSI procedure. How we will provide that? By referring to the GEM analytical vulnerability assessment guidelines. This is proposed a suite of robust methods, practical for everyday use, for the derivation of analytical seismic fragility curves and vulnerability functions, accounting for regional differences and cultural factors for the classification of building typologies and characteristics. So it really takes into account the global needs and the global perception and the diversity that we have in different countries on the globe when it comes to school infrastructures and it comes to determining their vulnerability. The guidelines, which were developed and designed in 2015 within the global earthquake model framework, which is still ongoing and that you can access at GEM online, they are designed to enable users like you to create simplified nonlinear structural models to determine the vulnerability functions pertaining to structural response. We have put the emphasis on low mid-rise building with load-bearing structures made of reinforced concrete frame or unreinforced masonry structures or different type of masonry structures. So this, together with the GLOSI resources online, would allow you to perform the steps that we will illustrate in this in the rest of this course this afternoon. Just to summarize what these steps are, the first steps is the truths. So this is what the roadmap is. We need to define the index buildings, and we have done that already through the previous lectures and through the previous assignments that we had provided. The next steps is to identify or select what type of models we want to build for a given analysis. The different models will depend on the complexity of the computations, but also on the type of information that you might have relating to that model, or relating to that particular building or building typology or building index. And this will depend on also not just the data, but also your ability and proficiency. The simpler the model, the larger the number of assumptions, and the larger the uncertainty that you make. The more detailed the model, the more close to the real behavior you might arrive to simulate. So once that is done, we then need to define the type of the level of how we define the damage thresholds for each of these index buildings or building types. So we need to have a quite clear damage structures in order to understand, once we apply the loads or once we apply the seismic action, what is the performance of the building. In order to do that, we can refer to various guidelines, both that are available nationally or internationally. We can define different level of damage, from no damage to complete damage. And this will allow to identify along the capacity curve, which you will find out what that means a little bit later on in the course, what are the different states. So in which state is my building, and how do I represent that with respect to reality? And that then allows us to determine what the performance of the building in relation to the type of analysis that we can run. The type of analysis, again, can be different. We can go from a nonlinear dynamic analysis to a nonlinear static pushover analysis, which is what we will concentrate on this afternoon, to very simple simplified mechanisms model, or just simple, more simplified pushover analysis. Finally, we get to the point, again, this will vary in complexity, and depending on the type of analysis that you will run, we will get different type of responses of different refinement. And again, this afternoon, we will concentrate on the nonlinear static methods and how we can use the nonlinear static methods to understand the performance of index buildings. Finally, we will look at the fragility and vulnerability. There are different options in order to bring together the fragility and vulnerability functions. And this depends, again, on how we want to treat the uncertainty and how we want to determine the different modes of failure and the different stage of failure. So fragility is the propensity of an object to be damaged by external agent. In engineering risk analysis, a fragility function expresses the probability that an undesirable event, i.e. a given level of damage, will occur as a function of the value of some environmental excitations, whose occurrence and magnitude are also affected by variability and uncertainty, i.e. we are applying a probabilistic approach to both the occurrence of the hazard and of the event and the magnitude of the response and the effect on the building. Fragility functions can take many forms. They can be derived as the density functions of performance of sample buildings, or as a density function of the many responses of index buildings to a large number of seismic actions. In the particular examples that you will see, we will take these later definitions, and therefore we will start from taking a representative buildings, what we call an index building, exposing it to a capacity, to a pushover analysis in order to define capacity curves. The capacity curves, by considering a large number of nonlinear natural response spectra, will be interfaced with the idealized nonlinear capacity curves, and this will determine a family of different performance points, which will be then analyzed in relation to the threshold that we had taken into account in the first, earlier on in defining the behavior of the structures, as you can see here, and the thresholds then, oops, sorry. And the thresholds, then this, we will use some analytical formula in order to arrive at a family of different fragility functions, which basically tell us what is the probability that a given intensity of that a given earthquake represented with a specific intensity measure, for instance here, P-ground acceleration, has a given probability of occurrence for a different level of damage. And that said, I think it's time to go more in details in the next lecture, the GLOSI fragility and vulnerability methodology. Thank you for listening so far, and have a good rest of the course.
Thank you very much, Dina. I will proceed with the next presentation. And now I am sharing my screen. Okay, well, Dina already showed like the framework on how to develop the fragility and vulnerability function. So I am going to focus now on this presentation on the GLOSI framework and what we did as part of GLOSI. So first, just to recall, the GLOSI library of school infrastructure includes several steps, as Dina mentioned, the taxonomy, the data collection, the country data, and all of this is used then to obtain the catalog of building types. And with that information, then you can derive the vulnerability and fragility, which you usually calculate in order to then assess the risk level and propose vulnerability reduction solutions that at the end are a retrofitting of the buildings. So if we go to vulnerability and fragility, just to recall, as Dina mentioned, we have fragility and vulnerability functions as two different ways of showing how a building will behave when some hazard intensity parameter is given. So for the fragility function, we will have different damage states. In this figure, you can see 4 damage states, and for each one of these, we will have one function that relates the hazard intensity parameters with a probability of exceedance of that particular damage state. So this set of functions will be the fragility functions that characterize the behavior of a particular building. And another way of seeing this is as a vulnerability functions, in which you will only have one curve that relates the hazard intensity parameter, but now with a mean damage ratio. So you will have a mean represented by the continuous line and a variance represented in here by the dotted line. So with that in mind, this is the proposal of the GLOSI framework to derive the fragility and vulnerability functions. In here, in particular, the main objective of this method is to make it a simplified method to obtain these fragilities that could be replicated in several places around the world. And it starts with the hazard definition. So the first step is to define the hazard. To define this hazard, there are several methodologies in literature for the particular GLOSI framework. It is proposed to use the FEMA P695 a set of ground motions. In this document, FEMA proposed 2 sets of ground motion, the far field and the near field, with specific characteristics of each one of these. And you can select one of those to perform your analysis. Also, this can be modified. If, for example, an analysis is done in a particular region, then you can characterize the seismicity of that particular region and select your own ground motions recorded inside or in other sites, but that have like the characteristics that you need for the particular region that you are analyzing. But in here, we are going to show you, and we will use in the next presentations and in the hands-on, the far field ground motion set as a way of using some generic or world-wide applicable set of ground motions. The second step is the definition of the index buildings. For this, in the GLOSI framework, the proposal is to use the GLOSI seismic taxonomy, which is comprised by 12 parameters. The first, or the three main parameters, are the main structural system, the height range, referring to the number of stories, and the seismic design level. Then there is a set of secondary parameters related to the diaphragm type, the structural irregularity, and so on. And at the end, you will have some intrinsic parameters that refers to the geometry of the building and the material mechanical properties. So in the framework of the GLOSI, you will find a catalog of building types that are available in the web page of the GLOSI, as I will show you in a few slides. And you can see for each one of these building types, the particular vulnerability functions, the fragility functions, and how well all the parameters that were used to estimate them. When we talk about the intrinsic parameters, and as an example, I will show you this RC building. This is an RC3. RC3 is a system that refers to a moment resistant frame, a reinforced concrete building that generates a short column because of the configuration of the non-structural walls in each one of the facades. So this is the taxonomy string, and for a particular building, then you need to define the intrinsic parameters in order to obtain the vulnerability function. And the intrinsic parameters in this sense are referred to the distance between spans, all the geometrical characteristics, the internal reinforcement considerations and characteristics of each one of the elements, and also the mechanical properties of the masonry infill walls and the mechanical properties of the reinforced concrete elements. Then now you have your hazard, you have also the building and the characterization of the building. Then you need to make a structural analysis, a 3D nonlinear model, and in here we propose a static approach because of its simplicity to be applied. As Dina mentioned, there are other type of analysis, such as a dynamic analysis, for example. But in here, if we concentrate on a pushover curve, we can also obtain very good results in this type of particular school buildings. And a pushover curve at the end is only a relation between the displacement of the roof and the base shear of the building. So you will have at the beginning of this pushover curve slight damage, then you will continue like damaging the building. Now you can obtain, when the curve start to bend, a moderate damage, then you can identify where the extensive damage is going, and finally the complete damage or the collapse prevention condition. So you need to characterize this, in particular for the RC building example that we talked before. We can do a numerical model of the index buildings. There are several software for this, and in the framework of the UNESCO Chair courses, we already given a course in which we show how to use OpenSys as one of the softwares to develop this type of analysis. And you can then characterize a capacity curve such as this and establish the different performance thresholds for each one of the damage states. In particular in this capacity curve or pushover curve. And then with the pushover curve, we can obtain the EDPs, the engineering demand parameters, that at the end refer to some particular measurement that you can make. So for this, we propose the static procedure, as I mentioned, and Rohit will show you in the next presentation how to implement one of these methods, that is the N2 method. The idea behind the N2 method is to obtain the simplified seismic response through a nonlinear static analysis. It starts with the capacity curve, then you can go to linearize the capacity curve and make some calculations in there, and you will cross that with the demand, and the demand will be the spectrum related to each one of the ground motions that we obtain in the first first step. So you in here start to correlate the two things that we done in the previous steps. First one, the pushover, and then you will correlate it with the hazard to see how your structure will behave. And all the details on how to do this will be explained in the next presentation by Roy. And once you have these EDPs, then the next step is to derive your fragility function or your vulnerability functions. And for the fragility functions, again, there are several methodologies. And what you want to do is that you have a set of engineering demand parameters that could be, for example, the roof drift correlated to some intensity measure that could be the peak ground acceleration or the spectral acceleration. You have some threshold for each one of the damage states, and then you want to transform that into a set of fragility functions. And for that, there are some methods such as the least square methods, the generalized method, or some other. There are several research in this area. And as Anna in the presentation, in the second presentation that we have before this, is going to explain us how these methods work, and in particular how one of these methods will work, and she is going to teach us how to do that using a program that we have developed in this framework. And for the example of the RC building, we have in here the engineering demand parameters, and with these demand parameters and the threshold, we can then obtain this set of fragility functions. Two, in this case, for damage states, but for example, you can add another damage state or only use 3. It depends on the context that you are. For example, in North America, you will use some types of damage states. In Europe, you can use others. So it depends a lot on the context that you are. And this is also dynamic, and it can be modified depending on each one of the conditions. Then you can go to the vulnerability function. We already developed one way of showing the vulnerability or the behavior of the buildings against some natural hazard. Now you can do that in the way of obtaining directly the vulnerability curve. There are two possibilities. The first one is a building-based approach, in which you go from the fragility to the vulnerability. So then, like, you are going to develop, or you develop in the process, the fragility functions, and then you can define a cumulative cost for each one of the damage states, and you can convolute them all into one vulnerability function, which will work as a way of representing the behavior too. There's other type of more like more integrated approaches. For example, the component-based approach. In here, I am showing you a curve developed using a Monte Carlo simulation through a program that is named Fumbul, that is part of the Capra suite, that we already covered in a previous course again. And in this, at the end, what you do is not only to understand the behavior in terms of the behavior of a building in terms of only one engineering demand parameters, such as the roof drift, but in here you perform a nonlinear dynamic analysis, and with this data, then you can go component by component, and in components we refer to each one of the nodes, each one of the walls, and you see for each one of them what is the particular EDP that characterizes their behavior, and you can then integrate all the losses in that sense. And some considerations are needed in this process, for example, to understand the residual drift and the effect of the residual drift in considering when a building needs to be demolished or not. For example, the intensity level with no significant repair cost. In some cases, you can have that a slight damage will occur, but the owner of the buildings is probably not going to repair that because it is very slight, and you should need to consider this also in the vulnerability function, and also the maximum acceptable repair cost for total replacement. For example, if you need to invest around 80% of the cost of building a new building, then you will prefer to to replace the building and not to repair it. So all those considerations can be included in that sense, and then you can have a smooth out of the vulnerability function that are the functions that we know and that we can find in the literature. For our example building, the RC building that we presented in the previous slides, then you can see here the taxonomy string and how the vulnerability function can be calculated. And just to compare, in this slide, I'm showing 3 different vulnerability functions. One for unreinforced masonry. You can see in here that you have a very steep slope, that the vulnerability is very high. This means that for lower PGA or any intensity measure that you are calculating in here, you will have very high mean damage ratio. For example, to obtain a 50% of damage ratio, you will need only around 0.4 Gs of peak ground acceleration. This can be contrasted with a confined masonry building, in which for the same 50% of damage, you will need to reach 1 G as PGA to obtain that level of damage. You can see here that the slope is lower in comparison to the unreinforced building, and you can also compare with the RC building that we did in this example, and you can see that you will need around 0.75 G as a spectral acceleration in this case to obtain that 50% of damage, of mean damage ratio. So you will have, this is a way of characterizing the behavior to see how a particular building will respond against a particular hazard, that in this case is the seismic hazard. And just to recall, this is part of the GLOSI library, as I mentioned in the previous slides, and you can go to the web page that is this one presented in here. This is part of the World Bank Global Program for Safer School, and you can go to the GLOSI, you can go to the library, and you can find in the library several resources. If you go, for example, here to vulnerability, you can see each one of the steps that I just mentioned in this presentation, and that we are going to see in future slides in the next presentations. And you can also open the guideline in which we explain this in detail. Another relevant resource is that you can go in here, for example, to the catalog of building types, and you can see several building types, load-bearing masonry building types, and reinforced concrete. You can go into one of these, and you can then open the particular building with a particular fixed taxonomy, in which you can see some pictures and also a structural model. You can see all the taxonomy parameters, the different failure modes, and you can download the index building assessment. This is a form in which all the fragility and vulnerability steps or considerations are included. For example, all the intrinsic characteristics of these index buildings are presented in here, the material properties, all the loads and the modeling consideration, the pushover curves in each one of the directions, the collapse, like all the thresholds, the collapse prevention and threshold, for example, in here, on how this is seen in the model. And you can then see the pushover curves, the engineering demand parameters, the fragility curves, and at the end, the vulnerability curve. So all these online resources are in here. You can go and see them by yourself, and we invite you to enter and to see that. Now, we already show all the process and the different steps. We are going now in detail in each one of these, and I now give the word to Dr. Rohit Adhikari, that he's going to show us how to obtain the seismic performance assessment and the different ways of obtaining the EDPs. Thanks.
Thank you very much, Rafa. So let me share my screen. Okay. Now, looks good. Mhm. Okay, can I see it? Now, listen.
Yeah.
Okay. And can you check? And you can hear me? Okay. So, good afternoon, good evening, good morning to everybody, depending on wherever you are. So after the overview of the whole process of seismic risk assessment that Raphael has presented to you, now I will start with the step of seismic performance assessment. So that's the focus of my presentation. This is the contents. So I will give a brief background. Then I will show you the illustrations for Pushover analysis, the procedure. I will briefly talk about damage states and what those are and how to establish those. Then I will talk about the seismic performance estimation using particularly the N2 method, which is a capacity spectrum based method. Then I will present to you about the Excel tool that we have been using, or anybody can develop based on the N2 method. So before going into the detail of the N2 method, I wanted to give you a brief overview of what a seismic performance assessment methodology is. So we are particularly focusing here on the building structures. For example, this building over here. Get the pointer. Perfect. Yep. So the seismic action is the input to the structure, which is represented in engineering terms by the intensity measure, the PGA or the SAT1, and the then we carry out the analysis based on this input. Can you hear me better now? Sounds okay. Sorry about that. So with the input, seismic input, we perform the analysis, and we get the output, which is the seismic response of the building structure. So the input is represented by a suitable intensity measure, PGA or SAT1, and the output, that is seismic response of our building, is represented by engineering demand parameter, which could be the, let's say, which could be base shear or the shear forces on the stories or the displacement terms. For example, the roof displacement or the inter-story drift or even the floor oscillations. So this is the broad picture of what we are going to talk about here. So our structural materials, for example, the steel or the concrete or even masonry, all perform non-linearly during extreme loading. For example, if you see a stress strain diagram here, for low level of loading, the behavior is elastic in both cases, but under extreme loading, for example, the earthquakes, the material, the structures go into nonlinear range. So the design or analysis that is based on elastic analysis or linear analysis is not very reliable because of this nonlinear behavior of our structures. For example, in designing our structures, if we design within this realistic range, then our structure becomes weak, or it has low seismic capacity. So that's not good. And if we design it with the assumption of linear behavior for higher loads, then that's not also good, because we are overestimating its strength, because its strength goes like this, not like this. So this tells us that the linear elastic analysis is not appropriate and does not give us reliable results. Similarly, with respect to the loads, if we consider the seismic load, earthquake load is a static load, which increases monotonically in steps, for example, like this, which is the equivalent load or the static procedure that is codified in many of the codes historically. So that is the static process of load representation. But in reality, the earthquake loads are dynamic and cyclic, as you can see in this time history. So it changes the direction with respect to time. Therefore, there is the degradation, the accumulation of damage, and the change in the structural properties, for example, the vibration properties of our structures, and so on. So those effects cannot be captured when we consider static analysis, which is elastic and linear. So based on that, this slide shows the level of complexity in computation used in the analysis, as well as the accuracy in the methods. For example, the linear methods, they require low level of computational effort. They don't require expertise, like high level of knowledge is not also required. However, they do not yield reliable outcomes. For example, the linear static methods, lateral load or equivalent static procedure in the codes, the linear dynamic method is more reliable than the linear static, because here we at least consider the dynamic behavior of the earthquake, dynamic nature of earthquake, which is an example is response spectrum analysis. Now we move on to nonlinear methods, where we could have nonlinear static methods, which Pushover analysis is an example, and nonlinear dynamic methods, where the nonlinear time history analysis is the example. So by now, we have already understood that the nonlinear methods are the ones we need to use for analyzing our structures under extreme loadings, for example, earthquakes. So within nonlinear methods, we have the nonlinear response history analysis, that is also called NLTHE or nonlinear dynamic analysis, and we have the nonlinear static analysis, which we call nonlinear Pushover analysis. The nonlinear dynamic analysis is the most accurate method available in the practice. However, this method is extremely time-consuming and computationally intensive, even for a single ground motion record. So, which is not very practical in, for example, design setting or in analysis, unless it is theoretical or so. So, because of this computationally and time-consuming procedure, we want to have something simplified yet reliable method, which is we possibly have this nonlinear static Pushover analysis, where we use computationally efficient approach, but we consider the nonlinear static analysis nonlinear static and nonlinear behavior of the structure. We consider that. Still, we use the static analysis approach so that we save time and effort. So the focus of this presentation will be on the nonlinear static procedure, which is midway between the linear elastic procedure to nonlinear full time history analysis procedure. With respect to modeling options, Professor Dina already showed some of these in her slides. So we have different modeling options: SDF system, a single degree of freedom system, or multi degree of freedom system, stick model we call it, or we could simplify our structures into number of planar structures, or we could go into 3D model. But that also has implications on our results. For example, this slide shows the effort versus uncertainty in the results. So the computation effort increases as we go from single degree of freedom system to full 3D model. Similarly, the reliability in our analysis results increases from lateral force methods to nonlinear time analysis methods. Now, as I told you already, we will focus on nonlinear pushover analysis in this session. So pushover analysis is a static nonlinear analysis method where building is modeled into a numerical model, which is subjected first to the gravity loading, the deadline live load, and then we apply a lateral load pattern, which is monotonically increasing until we get a failure ultimate state, which we call collapse. So the lateral load may represent a range of base shear induced by off-peak loading, and its configuration, its pattern might be proportional to the distribution of mass along the height, the mode shape of the building, or other practical means. There are several methods of pushover analysis available in the literature. As I said you already, the material nonlinearity is already assigned into the numerical model by either using discrete hinge locations or distributed plasticity. The FAMA 356, for example, gives these criteria for modeling these structures, reinforced concrete or masonry structures. And very important point here, this method of nonlinear pushover analysis is applicable only to low-rise buildings, these short period structures where the higher mode effects are minimal. And these buildings mostly behave in the first mode set displacement profile. So the steps of pushover analysis, after we conduct the pushover analysis, we get a static pushover curve as shown by this blue curve here, which represents base shear versus the roof displacement in this case. The results provide insight into the initial stiffness of the structure, how stiff your structure is, this line here. When your structure yields, for example, when it starts losing its strength, when it starts to crack, or when the reinforcement starts to bend or anything. So that's the yield point, for example, here. How far the maximum strength reaches in the nonlinear range, and how much ultimate ductility we have for our structure. So even this simple pushover curve can provide a range of useful engineering parameters that can implicate our design or analysis. So here this just shows a snapshot of how the pushover analysis looks like. We model the building 3D structure. We gradually apply monotonically increasing load pattern on the structure. We record the base shear versus the top displacement. We plot the results and then we get the pushover. So the steps for pushover analysis, just a brief overview. We model the structure using, for example, we could use the software, for example, SAP 2000 or OpenSys or Seismic or any other available methods, for example, the Planet 11 packages. So, and the modeling approach depends on what methods you are using, which software you are using. For example, here we are modeling a reinforced concrete building where we are using nonlinear beam element with concentrated plasticity at both ends. So these plastic hinges are represented by this force moment curvature relationship. So these are also available in codes, how to define those, and so on. So this is just one approach of creating the numerical model of the structure. Then we apply the dead load versus certain live load. Then after we finish the numerical modeling and then we apply the gravity load, then now we start applying the incremental load pattern, the lateral load pattern. So here in this particular session, I'm giving you one example of how to get this lateral load pattern. For example, we first analyze this building using the model analysis or eigenvalue analysis, where we get the mode shapes. And we identify there that this is a low-rise building. This mainly deforms in first mode shape as shown here. So that means the force profile also follows this displacement profile. The force distribution is also following this displacement profile because the displacement is proportional to force. That's our assumption here. And this assumption is valid for short period low-rise structures. But not only this displacement profile matters here, because the force is also proportional to the mass. That means we need to proportionate this displacement profile, but with respect to the mass of your flows. Because more the mass, it attracts more force. Therefore, the force vector, the lateral force vector we get is the outcome of this mass matrix times the displacement profile, the first mode shape profile. That's how we get this lateral force pattern here. So you just get this vector, and then you can start monotonically increasing it to whatever value it takes until the collapse occurs. Okay, you can multiply this by 100 times or 1,000 times, and then you can keep on increasing monotonically until you get the collapse. Can you mute Asan? Sorry. So this is just the procedure for Pushover analysis, record the base. So you gradually keep loading your elements, the elements you have defined in your structure. They start to get damaged. For example, the crack in the concrete occurs here. So your pushover curve is up to here now. So you keep on increasing the load. You get damage in more than one element, and some elements are already in the nonlinear range that you can see here. You keep on increasing, more elements get damaged, mainly in the ground story. Okay, then this is the ultimate stage where you can define your building has now collapsed, because so many of these beam column have already gone into nonlinear inelastic range. So you can define this point. Okay, this is my collapse state. So that's how you conduct Pushover analysis. Now, for this particular building, this is one school building example from Nepal. So multi-story school building. This is two-story masonry school building. So for this, I used the applied element modeling technique to carry out the Pushover curve, Pushover analysis, and this is the output Pushover curve. This is base shear versus displacement. But this is in absolute term. This is kilonewton meter. But for our purpose of analysis and for general understanding and for comparing different buildings in terms of their Pushover curve, we want to make it relative. We want to divide the base shear by the weight of your mass, seismic mass of your building, so that we get the base shear coefficient, which this is equivalent to the acceleration term, so that we can compare this to, for example, the acceleration spectra from the real earthquake or from the core. So that's the purpose of translating this absolute quantity into relative terms, so that we can compare and then we can perform analysis. I will come back to that later as well. Now, after you get the Pushover curve, doing the Pushover analysis, now we need to also define the different damage scale and damage states along your Pushover curve, because after you do the pushover analysis, you already have the idea of, okay, when does the collapse occur? So you did your pushover analysis up to the collapse point. So this is the collapse state. Now, where is my slight damage? Let's say few elements, minor cracking, hairline cracking. So this is the slight damage where your elastic region ends. So you were in the elastic range up to this point, but now you are slowly moving into nonlinear inelastic range. After you pass this point, you will not, there is less chance that your building will return to its original position. So that's the slight damage state. The moderate damage state is where many of your elements, the structural elements, have formed cracks or little bit bending in the rebars, but there is no significant damage. You could still repair your building. So we can say this moderate damage state is where I can repair my building. Okay. Now, after you pass that stage, there is extensive damage state where your building has suffered extensive damage, like a few millimeters cracking, cracks everywhere, diagonal cracks here and there. But your building has not collapsed. Your building is still standing and no life is threatened. Okay, so that's, we call it the life safety limit. So up to this point, you are still within the life safety limit. So that's at least good. So beyond this point, we are now moving into collapse state where life is threatened now. Life and economy is threatened. So economic items, for example, the damage will also translate into loss. Can you mute yourself, please? Rafa, are you there?
Yes.
Can you help me?
It's muted now. It's muted now. No problem.
So, so these are the different damage states. So here we are using slight, moderate, extensive, collapse. This is one scale. You could have different scale having only few damage states. Okay. For example, the US system has a similar scale, but they call it performance level. So operational level, which is equivalent to the slight damage state I was talking in the previous slide. The immediate occupancy limit, where your building is repairable, you could come back into the building and use it as normal. Okay, immediate occupancy. So that's the moderate damage level. Okay, still safe. Life safety limit, your building has suffered extensive damage. Life is not threatened, but your building is very hard to get repaired. Okay, now you might need to demolish your building. So that's already extreme level of damage. Now collapse prevention limit is which is equivalent to near collapse state. Now it's collapsed. You should never enter that building. You should plan to demolish it as soon as possible. No repair option is there. So the Eurocode has only 3 damage limits, but we can always translate one damage scale into another. We can always correlate those different damage states. So this is the definition I was talking about in the previous slide. So I'm not going to repeat that. So here, this slide shows for both reinforced concrete and unreinforced masonry or infill walls, the definition of physical damage state. So what does immediate occupancy or life safety or collapse prevention means? So it's, as I was explaining, minor hairline cracks. Okay, immediate occupancy, life safety, extensive damage to different elements, and so on. So you can go through these definitions on your own. Sorry, can you mute, please?
Azure.
Okay, sorry. So here again, the definition of damage states. I hope you have already got clarity on different damage states. So you can go to these details on your own. Now here, so the damage states are basically the physical states of the building, whatever damage it has sustained. Like if you see that building, you can see cracks, you can see the elements damaged or collapsed or anything. But in damage. We cannot represent the physical damage, or we cannot represent that directly into numerical terms. So what we use is, so what displacement, what deflection in the building means, or takes that building into that damage state. So we need this engineering parameter, that is displacement or deflection. For example, the roof displacement or the inter-story drift ratio. So those limits we needed in our mathematical numerical analysis. So different code or the standards, PMI standards, recommend these values, or you could go into literature to find these limits or thresholds for its different damage states for your particular building types that you are interested in. So for example, for the reinforced concrete buildings, the inter-story drift ratio of 2.5%, that means your building is already in collapse state. If your inter-story drift ratio is more than 0.5%, then you are already beyond moderate damage state, and so on. So these numerical values of drifts are very important indicators of the damage states, and we need to use these into our numerical analysis. We will come back to that later as well. So this is how we correlate the global and local damage states. For example, in the Pushover curve, you have different global damage states marked, but each of those global damage states have meaning in terms of the physical damage in your structure. For example, the local element level damage. For example, the green point here is global slight damage, which means here that your local elements are yielding. For example, your concrete has cracked, your rebars are yielding the columns in the ground story, and so on. So this slide shows a typical example, one example of what does the different damage states look physically in real buildings. For example, this is slight damage here, minor hairline cracks in few elements. Here, the moderate damage, the crack width has increased to, let's say, 3, 4, or 5 millimeters, let's say, and the extent of cracking has expanded to more elements. Extensive damage, you can see cracks everywhere, wide-on cracks, and so on. So collapse, where you have very extreme cracks and fully formed cracks, which is never repairable, and your building should be demolished. And these elements could collapse anytime. So these are what damage states look like in reality, in physical basis. But as I told you already, we need numerical quantification of those limits of different damage states. Now I will go into the N2 method very quickly. I'm not going into the details of the numerical or mathematical models theory behind those, but I will make it in a practical way so that you can understand how to use the N2 method. So the N2 method is based on the capacity spectrum method, which was developed early in 1970 by Freeman, and this was implemented in several US standards, for example, ATC or Freeman. So N2 method particularly is developed by Pfeiffer around 2000. It has been implemented in Eurocodes. It has been used widely by the practicing engineers or researchers in the academic setting. So in this method, we get the multi-degree of freedom system capacity curve, then we translate it into equivalent SD of single degree of freedom system. Then for this, we generate the inelastic response spectra. Then we compare the strength versus the demand to get the performance point. So these are the different steps for the the N2 procedure. We first to convert the MDF system to SDF system. This is the Pushover curve you have originally. Now to convert it into SPF system, we need to get the equivalent mass for the SPF system using this. So M is the mass, Y is the Morse vector. We calculate the transformation factor to transfer the MDF system into SPF system, which is the maximum value is 1. In step 3, we reduce down the base year of the MDF system into the base year of the SPF system by the transformation factor, and similarly the roof drift or displacement by the transformation factor. To do this simplification, we need to idealize we need to mathematically idealize the given Pushover curve, because the Pushover curve you obtain from different programs will have any shape. So we need to idealize either bilinear or trilinear or multilinear idealization. Here we use bilinear idealization, and here you can see different codes or standard different idealization. So bilinear idealization is what we use here, which is based on equal energy principle. Okay, our idealized curve, the area under our idealized curve and the area under the original curve should be roughly equal. That's the principle of this idealization. So we have equal energy principle here. That's how we idealize the Pushover curve. After idealization, we convert it into SPF system Pushover curve, and now we need to get the response spectra. This is how they get the response spectrum. So for a natural ground motion, we get the response, the acceleration response for different period. Then we plot this over here for a number of ground motions. Then we get the smooth response spectra, and this is how they develop this spectra, code spectra, that is available in different codes. So this is how we get the response spectra. So we generally have the response spectrum in acceleration versus period of reflection terms. We need to translate it into ADRS format. Okay, acceleration versus displacement format using this equation. This is the dynamics. I'm not going into the theory behind. So this is the elastic response spectra of the given ground motion or from the code. Now we need to get the inelastic spectra based on your structure's property, the response reduction factor or the ductility factor of your structure. And this is the formula to reduce your elastic spectrum into inelastic. Okay. Then we compare our Pushover curve, the SDO Pushover curve, with the inelastic spectrum to get the performance point. And this depends on different conditions. For example, your period of your SDF system is greater than the corner period of your given ground motion or code spectra, and so on. So there are 3 different conditions, depending on which we use different formula, or we can get the points graphically as well. I suggest you to go into this paper to understand the theory behind this formula and how to compute these points, because I have no time to go into details here. So as I told you, there are 3 different cases to get the performance points. Now, for this given building, for which I showed you this Pushover curve already, I'm going to demonstrate you how to use the entry method. We are giving you an Excel sheet that can compute this performance points for different ground motions using the entry approach. Okay, so the data given here are: this is your building. Okay, the story height 3-story, story height 2.814, story masses I have already computed. Okay, so this is first story mass is more because I'm considering half above and half below. Okay, and the top story mass is only the half story here. And I'm also giving you the first mode set because that's what we use for getting the lateral load pattern. So this is 0.67 and 1. So 0.67 and then 1. So this is the first mode set. So we are going to find out the IM versus EDP. IM means intensity measure, that is PGA. or SA and EDP, that's engineering demand parameter, which represents your output of your structure. For example, the interest drift ratio or the displacement. So in Intrometer, so these are different screenshots from Intrometer. I have pasted you for your reference later, but now I will move on to the into Excel sheet. Give me one moment. Yeah. Give me one moment, please. Yeah. So we are going to provide you this Excel code. Yeah. I'm okay. One second. Opening. I need to see it. Give me one moment. I will see it now. The Excel. Okay. So this is the Excel sheet. You can see. Close this. Okay. So this is the Excel sheet we have developed, and we will provide you for the application of the entry approach. So for that particular building, I told you, I gave you the story height is 2.814. Okay. The number of stories is it's 2-story building. So you can choose how many stories you have, 1, 2, 3, 4, 5, 6. So one note here in this Excel sheet, only change the input in the blue colored cells. So you can only change the inputs. You only need to change the inputs in the blue colored cell. For example, this story height, the number of stories, the mass of your different floors, and this one, and also the capacity curve. So the capacity curve I have given you. I showed you in the presentation. So I have pasted those data for that capacity curve into this. So you can paste the capacity curve here. That's the first task you can do. Okay. So come and paste. First, remove everything, whatever there is already. Delete everything, and then copy and paste the data here. Okay. And these cells you don't need to change anything. So, but here, this cell, if your data is more than 761 cells, for example, if your data comes below as well, then you need to double check this cell. So this column computes your equal energy principle. So that helps in the computation. So you need to, if you have longer data than this one, then you need to double check your formula is still there in this cells. For example, here you can see this formula. So if you go down, for example, if you go down, you can still see formula here. So we are safe. Okay. So if you go down, if your data is, for example, up to here, then you don't have formula here. So you need to go back here and then pull it down till your formula is your data. Okay. If your data is coming up to this cell, then you need to please pull down this formula until your data point. Okay. Hope that's clear. Now you can. So after you change this story height, number of stories, you can input this story masses. You need to compute this, or in our case, we will provide you this data. And you also need to give the mode set vector, because the mode set vector will control the lateral load profile and so on. So here, in graphical terms, this is the original given a multi-degree equivalent system pushover curve for your building. This is equivalent SDF system. This is equivalent SDF system. Then this is the bilinear idealization based on the equal energy principle that I was talking about. Now, one thing you need to note here is you can play with this number. Okay, this is percentage FU. So your yield. So this bilinear model, we call it elastic, perfectly plastic model. Okay, this is elastic branch. This is perfectly plastic branch, and this is what we call the yield point. Okay. So this point, so if you change this, So this number means what percentage of the ultimate strength you want to consider your yield strength of the idealized curve. So for example, if I change it to 0.8, so 80%. So my yield capacity of the idealization is only 80% of my maximum capacity in the original capacity curve. Okay. So we don't want, this does not look right. Okay. You keep playing, you will understand. So even if you go 90%, this does not look right because you are overestimating your initial stiffness, like significantly. If you go to 0.95, it's getting better, okay, but you are still overestimating your initial stiffness. So if you go 0.98, then you are now, it looks good. So that's how you need to play. We will take questions later. Okay? Yeah, we can do that. So I will respond to your questions later. Okay. So this is how you need to play, and you can source literature about the bilinear idealizations and how it affects your results. So that's your input. For the input ground motions here in this particular course, we are giving you 22 set of FEMA P695 far field set of ground motions. These ground motions are collected from worldwide seismic events, Taiwan, Japan, US, Europe, and so on. And these are, so when you consider these 22 ground motions, then you get average results or envelope of these results. Then you are considering a number of spectral properties into your analysis. So that's a good thing. That's why we are considering this 22 set of ground motions for our analysis. Okay. So now if you go to next sheet, graphical N2, here these graphics are for our visualization, and it's not affecting any particular results in our analysis. So you can keep, again, I told you, you can change things in the blue cell. For example, you can, from this drop-down menu, you can select any ground motion and see how that result changes for different ground motions. And for 22 ground motions, we use scaling for each ground motions to cover a range of the acceleration capacity for that particular ground motion. We scale down, we scale up so that we get enough and sufficient points for our fragility derivation. So for each ground motion, we are scaling like more than 20 times. So we have like several hundred data points finally. So there is a T, the corner period. Okay, I need to mention that. So in input ground motion, there is this corner period that is used in the N2 approach, as I was showing you in the slides. This corner period plays important role. For example, if you are given let's say Code spectrum, then you already have a clear corner period. But for natural ground motions, it's very hard to identify corner period. So we have already listed here the corner period for this particular ground motions, but you can double check and then you can modify if you want. And similarly, you can get the corner period for different ground motions of this choice. So here you can play with those as well. You don't have time to go into those all details, but the most important point here is if you take this EDP generation, engineering demand parameter generation, for all your ground motions, all your scaling. So all the computation is done at once when you click this button. Okay. So if I click this button now, okay, micro is not enabled, so I'm in Zoom, so I cannot run it. But if you click this run EDP generation, it will run in your system. Okay. So wait until it finishes the run. Okay. Then afterwards, you can, when it finishes the run, the program stops. Then your results are now plotted in this sheet, the EDP sheet. So here is PGA, here is the SDI, that's root displacement of your structure. And here is also SA, the spectral oscillations, because you can consider your intensity measure to be PGA or to be SA, depending on your structure or your choice. So here, this is the plot of this IM versus EDP results obtained from the N2 method for all the ground muscles for so many scaling for each ground. So this is PGA versus SD, the root displacement, spectral displacement. And similarly, this is SA versus the SD. So you could use, so whatever your IM is, either SA or PGA, you can use your these into your fragility assessment, which Asana will talk about in the later presentation. So let me quickly go back to my presentation now. Give me one moment. Let's see. Presentation. So, yeah. Okay, so that's how you apply the N2 method Excel sheet. So there are other methods. I'm not going into details, but just I'm naming it so that you could go into this literature and then read about those more. So these are based on nonlinear time history analysis, which means already more accurate and more reliable than the N2 approach. But these are computationally intensive, and these also require high level of knowledge. So I suggest you go into this literature and then read about this different cloud analysis or incremental dynamic analysis approach or multiple strike analysis approach. This is a summary, just a summary of what we covered in this presentation. No need to spell it out. So I will now pass on to Asana. She will discuss about the introduction and methods for fragility derivation based on the performance point we generated from the N2 approach. Thank you. Okay.
Hello, everybody. I think it's been almost 1.5 hours. If you want to have a short break, we are running a bit late, so maybe a 2 minutes break, and then we'll start the presentation. Hello, everyone. We are back to the presentation. As we're running a bit late, I would try to make it as quick as possible. We can have a question and answer session in detail tomorrow because we will be presenting a hands-on task at the end of today's presentation. So as we discuss the results of that task, we will have opportunity to discuss things that are probably not clear or we rushed in today's presentation. So this is from where Rohit has left off. We are dealing with the fragility assessment. We have reached the stage where we have the performance points. So what is a fragility function? It's the likelihood of damage given a certain level of ground motion. So each of these curves that you see here represent a particular damage state. Okay. So in terms of probability, you can say that this is the probability that the demand is exceeding given capacity of a structure at a particular IM level or the intensity measure. So if we go ahead, this is what we have been talking about so far is about analytical fragility functions. This is density functions derived from the cloud of performance points, as we have seen in Rohit's presentation. And this is the good thing and advantage of this method is that it can be used for any building type, and it can be extended to the level of accuracy as we want. For example, you can include more variability in the modeling aspects or in the ground motion uncertainty or in terms of any sources of uncertainty that we want to consider. Again, that is also the limitation because the accuracy of these results would be dependent on the factors that are used in deriving the performance points. There are other methods of fragility functions, such as the empirical post-earthquake data-based fragility functions, which we are not currently dealing with. Also, there are other methods which are used in different locations. So just to make it really short and clear, we now have the performance points. We have defined the performance thresholds that Rohit has defined, either in terms of damage states or performance levels. Now what we need is a regression analysis to connect the performance points to the probability of exceeding a given damage state at given IM levels. So what we want to achieve is this. We have the set of performance points. The damage thresholds are defined in terms of the EDP, that's the engineering demand parameter, could be the rooftop displacement or the drift or any of the parameters that we have used. Now, how we define very often the fragility function is usually used we use a log normal cumulative distribution function to define derive and define these fragility functions. This is the formula, the standard cumulative normal distribution. We have two parameters here, the alpha and beta. So this is the median of the fragility function. That the alpha would give you the IM level at which IM level at which 50% exceedance chance for a given damage state. And beta is the standard deviation or the dispersion of the fragility function. Now, in order to derive this from the given performance points, we use regression analysis, any statistical approaches that are suitable for this purpose, such as the method of moments or maximum likelihood and so on. So we would briefly look into the three methods, and then we would go a bit more detail into the least square method. And we would also be giving you tools to perform the least square method, just like the Excel tool we previously explained. So here we have the first method, which is method of moments. It's the most simplest method because you have the performance points that you derived from an incremental dynamic analysis or an N2 method. So you have basically the IM points. This is only applicable when IM at desired performance threshold is known for all the data points. So for the same reason, it may not be applicable to other cases where you have empirical data, or you have a truncated IDA, or you have multiple stripe analysis where you would pre-select IM values at which you are doing the analysis. So that is a limitation for this. And still, this is a very simple method. What you do basically is get the sample mean and get the sample variation. So that would be defining your parameters of your fragility function. It also has limitations. This would only capture the midpoint or the central point, but it's not very accurate throughout the distribution. The next method is maximum likelihood. So instead of directly calculating the sample mean and the variance, we would now assume a certain variation from here. So this what we do in this case, it is possible to do for both analytical and empirical methods. So it doesn't depend on whether you have all the points available. So what you do is we are trying to maximize the likelihood of our fragility function, defining the kind of the data points that we obtained. So what we have is if you see the number of collapses, that is the small ni, in a total number of ni buildings, that would follow a binomial distribution. So with the parameter pi being the log normal CDF, because we are assuming again that this is a log normal function. So now we have for one particular IM I, if you take a product of all the IM values, that would be your likelihood function. So you want to have the fragility parameters such that maximizes the likelihood of obtaining or observing all the small ni, capital Ni pairs. So you got the likelihood function, you can maximize it to find the two parameters mu and beta, which are again function already included in the PI. This is again another method. This is generalized linear model. Here what we do is first segregate or convert the data into a binary format where for each damage state, you check if that damage state is exceeded or not exceeded. So for example, if it's collapsed, if the building is collapsed or not collapsed. So you would have from the dispersed performance points, you would have a format that is 0 or 1. And within that, you would then fit a linear model. For this purpose, there are some link functions used, such as a probit function or a logit function, which then leads to linear pattern again, where you have two parameters, theta naught and theta 1, which can be then obtained by the same maximum likelihood estimate that we did earlier in the previous method. So you can check this literature, the GEM guidelines. This suggests to use either GLM or the least square method, which I'm explaining next. So this is the least square method. What we do is again a regression of performance points to provide the probabilistic relation between the EDP and the IM. So in here, what we try to do is minimize the error between the predicted fragility function and the regression line that we are doing, or the error between the least square error that we use to regress. Okay. Sorry, do we need? Yeah. So in here, what we do is we segregate the data points into different ranges corresponding to different damage levels. Thresholds that we have defined, and we choose the IM levels such that at least half of the points are above your threshold and half of them are below the threshold. And again, we assume that these points within the range are distributed log normally, and we have the corresponding CDF function that defines your fragility function. So in here, we do this in a piecewise manner. That's because you're not regressing a single line over the whole range. Instead, you have different lines with different slopes and median values for each of the range. That is captured through this regression equation. So you would do a least square method to get these coefficients A and B, or L and B, which is the intercept and A is the slope, from which you would then calculate the parameters of the fragility function, the mean and standard deviation. So this is the method. We can explain how we actually perform this using an example. So this is an example of a confined masonry building, which has a better seismic performance capabilities than a normal unreinforced and confined masonry building. So we have obtained the pushover curve as Rohit has explained using a numerical method. And then we can then idealize the curve, obtain the performance points, and then obtain the fragility functions. So in order to show how we derive the fragility functions, like maybe I can stop sharing and go into the Excel and MATLAB file. So as you've seen, we have given the Excel toolbox for the N2 method. For the fragility derivation using LSM, we have a MATLAB code, but you don't have to install MATLAB on your system. So this is generated in such a way that once you download and install it in your system, it will run even if you don't have access or MATLAB in your system. So let me go into the folder. So once you have, we will be sharing this with you right now in the chat box. Fragility derivation. So what you will get is this. Oh, you can't see now. Sorry. Let me share the screen again. Okay. So I hope you can see the screen now. Can somebody unmute and speak if it's not
Yes.
visible? Yeah. Okay. So what you would get is this zip file. So you have to download this and unzip the file, and it gets downloaded into your program files in the name of UCL. Okay. Yeah, you need to install the this zip file first, and then you can follow the instructions in the README file here. So install this MATLAB LSM fragility driver, the one that is given here. Then that will automatically install the required runtime environment. So you don't have to install MATLAB separately. Now go to the installation folder, which is the UCL folder. And then you have to first give security permissions to, sorry. Where is the folder? Sorry. Okay. So can you still see my screen?
Yes, we can see as another screen, but only the fragility derivation MATLAB program folder.
Okay, okay. So now I will show you. Can you see the UCL folder now?
Yes, yes, yes.
Okay. So first you need to do is you have to give permissions, full security, full access, and full control over this. So go to properties and give full security control for all users, just to be safe, if in case it's not allowed here. So you can't see? Oh, okay. So I think that is clear. You can just allow all users of the computer a full access. So once you have full access, you can open the UCL folder. Is that clear? Okay. Then you have 4 folders here. Open the applications. And then you have an Excel sheet here, LSM Excel SX, and this execution file is the MATLAB file. So you need to first open the Excel file. You can't see that, no? Okay, I think it's okay. So once you have this file open, you provide the details of your model. So the performance points, IM versus EDP that you have obtained from the N2 method, you would input here. Be very mindful of the units. So if you're giving IM in PGA so far, continue using that. And then EDP can be in meters, or if you're using drift, it would be in percentages. So just in the same units, provide the threshold limits here. That is for SD, MD are the different damage states we are considering. This is the thresholds that we have assigned for this particular building. So once you have that, you can also play with the other things in your blue cells, as Rohit mentioned. You can also increase the step size if you wish. And now you have this, save everything as you want, input everything as you want, and close the file. So after that, you can go back to the applications folder and then run your MATLAB file. So if you run this file, that will generate the fragility functions, but give it some time. It might take a few minutes, and then it will then show you a message saying you can see the results in the Excel file now. So you have to wait until you get the message. Once you get the message, you would have the functions, the fragility functions. Sorry, it's still opening. Can you see that? No. So once you run the MATLAB code, you would get the fragility functions in the same Excel file in the next sheet named fragility. Okay. So this was the first sheet where you input all the material, and this is the result where you get. So here, if you want, you also get the full fragility function coordinates, and here is the mean values of all the different fragility functions, all the 4 different fragility functions and the beta values. So that would be the end of your fragility derivation. I think things are clear. Once we are sharing this material with you, and you can play with 2 or 3 pushover curves that we will give you as inputs. So with that, I would now stop my presentation. For the lack of time, I will now give the screen to Rafa to continue to the vulnerability derivation. Thank you.
Thank you very much, Hasana. I will proceed sharing my screen. So I'm going very fast. I'm going to present this very fast. This is the different methods to derive the vulnerability function. So Rohit already showed us how to develop these engineering demand parameters, and Hasana presented how to pass from these demand parameters to the fragility curves. So now I'm going to explain you the last part of the methodology, that's the vulnerability function. So as I mentioned previously, there are 2 ways of obtaining these vulnerability functions. The first one is the component-based assessment. And well, I'm going to start with this one that is the most detailed one. And I will just explain it very fast. For this, you need first to establish a component model for your building, in which for each one of the stories, you can specify all the structural or the architectural and the contents elements. And for each one of the elements, you will assign them a particular fragility curve. But this curve is different from the one that Hasana just presented, because this fragility curve is for a particular component in a building, not for a building itself. And to obtain these, there are a lot of literature, but the main source of this type of fragility functions for components is the FEMA piece 58. And in there, they present a compendium of several fragility functions that you can also access through a tool that they have, that is the PACT tool. And each one of these fragility functions have several damage states. This one is for a node of 1 column, 2 beams, 1 in each side. And in this FEMA document, they specify what is slight damage, what is moderate damage, and what is extensive damage. And for each one of these damages, you can then assign a cost of like repairing that particular damage. So the extensive damage repairing cost will be very much higher than the slight damage repairing cost. And you need to do that for each one of the components. And there are also several methodologies. This is a paper developed by Jamin et al. In 2017. And they specify all the recurrent steps that starts going for each one of the records and each one of the incremental steps of the records. And you will then go for each one of the components and sum the cost of repairing each one of them from the fragility functions that, together with the probability of being on that damage state, you will have then a distribution of losses, and with that distribution you can assess the vulnerability functions that you can divide into the vulnerability function of the structural elements, of the non-structural elements, or of the content elements, or you can sum the three of them all into one vulnerability function for the total repair cost of the building that integrates these structural, non-structural, and contents repair costs. And I already mentioned this, just to recall it, you need to consider several additional things in this process, such as the residual drifts, the intensity level with no significant repair cost, or the maximal acceptable repair cost for total replacement. Then we can go to that was the more detailed component. I just mentioned this for you to have like a context on how to do that, and more literature. You can, if you are interested in that, you can go on the literature and see all the details. But in this case study and in this course, we are going to present the building-based approach. And for this, I already mentioned how to go from fragility to vulnerability, and the process is to assign cumulative cost for the repairing of each one of these damage states. And with that, you can then obtain the vulnerability function. And as part of the documents and the files that we are sending to you in a moment, you will find this Excel file that I am sharing at this moment. That is an Excel file that you can input the fragility function. As you saw in the previous step that Asana just mentioned, you can obtain the mean and the standard deviation for each one of the damage states of the fragility function at building level. So you just need to include in here those parameters, and then you will have the vulnerability functions and the fragility functions graphed in here. All of this is, of course, formulated. So the only thing that you need to change are these cells that I am coloring in blue. And to obtain the vulnerability function, you just need to assign a damage ratio per each damage state. So the first one is the collapse. For the collapse, you will have 100% certainly, because if the building collapses, then you will need to replace it. So the total damage ratio will be 100%. If you go for slight damage, that is this green fragility function. So you expect it to spend only around 5 or 10% at top of the total cost of the building to repair that damage state. And you will have these two additional moderate and extensive damage states that you need to assign the damage ratio depending on how you define that moderate or extensive damage. For example, it could be 40% in here and 65% in here. And with this, you will have at the end your convoluted vulnerability function. You can start changing things. For example, if in your analysis the extensive damage is around 80% of damage, then you can modify it in here and the vulnerability will go up in that sense. If you figure that the moderate is 25% of the repairing of a moderate damage will be 25% of the total repair cost or the total replacement cost, then you can assign these values and you will have this for a vulnerability function at the end. So we will provide to this Excel file, so you can take the fragilities from the files that Asana just showed, enter those parameters in here, and then start changing this damage ratio to convolute your vulnerability function. That will be the output that we wanted you to be able to do at the end of this course. So now I will give the word to Asana so she can explain the hands-on task. The idea now is that we will give you a Google Drive link so you can enter and download all these files that we presented during these sessions, and also a pushover curve for each one of the typologies. You will have one for each typology, as Asana is going to explain now. Or Rohit, I don't know if you are going to explain it.
Yeah, Rohit here again. Okay, I hope you can see my screen.
Yes.
No. Yeah, Yep. Okay, good. What we are asking you on this hands-on task is basically homework. So this is the instructions for the hands-on task. So you are asked to first conduct the seismic performance assessment to get the IM versus EDP points using the N2 Excel code we have given. For the same set of ground motions, you don't have to change. The inputs required for that Excel sheet, we will provide it. I will explain that in a while. So in step 2, you are required to use that IM versus EDP, the cloud of performance points, to derive fragility functions using the fragility MATLAB code that Asana was talking about. And in third step, after you get the fragility functions, you are required to use those fragility functions and the loss ratio into the vulnerability Excel sheet that Raphael was explaining just before. Okay, so we are giving you 3 cases of one is unreinforced masonry, one is confined masonry, one reinforced masonry, and we are requesting you to do this for all 3 cases so that we can see how different buildings perform for the same set of ground motions. Okay, so all the necessary input data files and the codes or Excel program we will provide you shortly in email and also in the chat. I think Rafa can see this now. Okay, perfect. Okay, and then tomorrow we are going to present a detailed discussion of these results from outside as well, so that you can compare your results against ours. So first case is URM building. This is a building, and we're going to explain the taxonomy behind. So numerical model using applied element method. This is how it behaves during the earthquake in long direction. This is how it behaves during the seismic loading short direction. Okay. Now, therefore, because this building does not have, this building lacks global box-like behavior, we want to analyze this building with respect to the in-plane and out-of-plane systems. Accordingly, we have derived the pushover curves and the damage registers for each of this in-plane system and then out-of-plane walls separately. And for this task, we are requesting you to get this out-of-plane wall, this pushover curve, these different damage registers, and then perform the analysis only for this out-of-plane wall. Okay, not for the building, not for the in-plane system, only for this, and we will provide data only for this. So you are only required to analyze the out-of-plane wall. Similarly, for the confined masonry case, we are giving you this building and this pushover curves, the damage registers, and all the necessary input data will be provided. And similarly for RC building. So you are required to do repeat the procedure for these 3 different building cases, and then get your results ready by tomorrow before the session. So before going into Q&A, I want to show you briefly about what the files we are going to send to you. So folder. Okay. I hope you can see my folder. So this is the data. So we are providing you the N2 method Excel code. If you notice here, a quick note, this has only output in terms of SA. If you want to use SA in your analysis, I think for RC, you can use SA. And for unreinforced masonry and confined masonry, you can use PGA versus the displacement. Okay, but this code, the second code, has both SA and PGA options. So feel free to use whichever code is applicable for your building case. Similarly, the fragility derivation, go through this README, unzip this folder, and then install it. Double click this to install. It installs whatever runtime is required for the MATLAB run. So you don't have to have MATLAB before, because this installs whatever is needed already. And similarly, the vulnerability Excel code Rafa showed you. So all the input required for these different programs to run is given here for 3 different cases I was talking about. So this is unreinforced masonry out of plane wall only. This is confined masonry that case, and then This is the reinforced concrete case. Okay. We have already shared this link, and we will also send this folder via email. Okay. So we can go back now to the question and answer. Few question and answer. I think we can cover the Q&A session after tomorrow's session, I think. Okay, can we check the chat if there are questions? Yeah, if you have any quick questions, like very relevant questions, you can unmute and ask, please. Okay, if you don't have any questions at the moment, you can prepare a question for tomorrow. I think we will have a longer question and answer session tomorrow after we discuss the results. You can compare your results with this. So you might struggle to work with those codes, but if you follow the instructions, if you follow these presentations, we will also share the PDFs of this presentation so that you can follow these PDFs while going through those codes. But you need to do some trials before you are ready to use those codes. Okay. But we want you to do that for all three different buildings, not only one, all three, on reinforced confined masonry and then reinforced concrete, so that tomorrow we can see the difference in results according to the typology. Okay, so no questions for the moment. The roof drift is the displacement, 1 second, or one question, of the last story divided by the total height of the building or divided by the height of the last story, total height of the building, because the roof drift is the roof displacement divided by the total height of the building times 100. That's the percentage drift. Yes, it will be available, but will take a couple of days. No. We are not able to upload it today because the video needs to get downloaded and then we need to upload it into the Epicenter YouTube. So you need to keep checking the Epicenter web YouTube page. Okay, we come back again at 2 p.m. tomorrow, and then we will discuss the results of the hands-on task. Okay, we will have the results with respect to original building and the retrofitted strengthened building. So it will be more interesting discussion tomorrow. So please do those 3 hands-on tasks. Okay. Thank you very much for attending. Thanks to everyone who spared their time to attend, and hope you enjoyed this session. So we'll see you tomorrow. Thank you very much. We are going to end this session now.